So now that we've defined relations, this very general object of a relation on A is just a particular subset of A times A. So this is an extremely general object. And it's maybe a little bit too general to be useful yet. But the benefit of defining it on sets means we can use all our set theory tools that we've developed in order to start doing more interesting things. So that putting things in terms of set theory allows us to use the tools that we've already developed. Okay. So, some properties of relations. What we're trying to do here is add additional structure to relations to make them more interesting and more useful. So, as I just said, a definition of relation is arguably too general to be useful. Basically, any subset of a Cartesian product is a relation. Now, in order to make that more interesting, we require some additional structure on that subset. So let's consider a couple of examples. If we consider is divisible by on the set of integers, this has some useful properties that we have already used when we're playing around with some of our basic proof examples earlier. Namely, for all integers n, we know that n divides n. And for all a, b, and c that are integers, if a divides b and b divides c, then we know a divides c. And that's not so hard to prove, but it turns out to be quite useful. And we may have used that already. I think we've used that either in homework or in some examples. Now, one thing I want to notice here is that this inequality, namely less than or equal to, has, on the set of real numbers, has quite similar properties. So in particular, for all x in R, so I'm just going to underline that and underline that, we know that x is less than or equal to x. And so this is quite similar, though the symbol is different and the context is different, somewhat quite similar to what happened here with divisibility. Again, if we take three real numbers, x, y, z, and we know the first is less than the second, and the second is less than the third, then the first is less than the third. And again, this is quite similar to what just happened with divisibility, namely if a divides b and b divides c, then a divides c. And so there are parallels between the properties of these relations, even though the relations themselves are defined quite differently and used in quite different contexts. There's some similarity going on that we would like to abstract away so we can say more general things about relations that have that property. So this sort of additional structure, this transitivity property here, this reflexivity property here, which we'll define in a moment, these make those particular relations more interesting and more useful. And so we want to understand those properties in abstract so we can say more general things. Okay. So here are three useful properties, two of which we just saw on the previous slide. So a relation on a set A is reflexive when every element is related to itself. So for every A in A, A are A. It's symmetric when, if we take any pair of elements, A, B, if A is related to B, then B is related to A. And so, for example, equality does this, but, for example, less than or equal to does not, nor does divisible by. Okay? But a couple of relations we know do this. Finally, transitivity, which again we saw on the previous slide, if we take any three elements, if the first is related to the second, and the second is related to the third, then the first is related to the third. And we saw that divisible by and less than or equal to satisfy these last property. And so if we look at some relations that we've already seen on the set of integers, we can summarize in a quick table here which relations we've seen. So strictly less than or equal to, not equal to, divisible by, not divisible by, which ones satisfy which of these properties. So for example, strictly less than is not reflexive because no element is strictly less than itself. On the other hand, any element is less than or equal to itself. Neither of these are symmetric because, for example, just because 1 is strictly less than 2 doesn't mean 2 is strictly less than 1. So that's why it fails to be symmetric. But it is transitive. If 1 is less than 2 and 2 is less than 3, then 1 is less than 3. Okay, so you can work your way through these. One thing to note is, of course, equality and not equal to, they are complements of each other if you look at them as subsets of a particular Cartesian product. And interesting that just work your way through some of these properties here. It's not necessarily trivial how one of these relates to the other. So it's worth thinking about these properties here and try to convince yourself of the elements in this table. So we can also draw some of these in pictures. What we're saying here with this diagram is that every element is related back to itself, that means it's reflexive. If it's symmetric, then we know that if x is related to y, then y is related to x. So there's an arrow from x to y, then there's one back from y to x. Similarly, transitive, if we know that x is related to y and y is related to z, then we must have that x is related to z. Okay, so we can summarize these relations with pictures like these. That just help build intuition about what's going on. So, some good examples that maybe we'll do in class. So we can let R be the relation is a subset of, which we can think about as being on all subsets of the integers, so on the set, on the power set of the integers. This is a good relation to think about to see, is this reflexive, symmetric, and transitive? Similarly, if we think about the set of people who are watching this video now, or perhaps when you're watching it, can think of the relation being lives within 10 kilometers of. So think about person 1, do they live within 10 kilometers of person 2? There's another relation that we maybe will discuss in class later. Okay. But one important relation that we definitely will spend time on is congruence. We've already seen a little bit of this. We did a definition of it a little while ago. So in particular, we should recall congruence modulo n, that if, let's see, if A is congruent to B mod n, then we know that n divides A minus B. Yes, that'll work. So A is congruent to B mod n means that n divides A minus B. Or if you like, A and B have the same remainder when we divide by n. And congruence modulo n is reflexive, symmetric, and transitive. Okay? So it's an interesting relation to play with because it satisfies all three of these properties. So we need to prove this. Okay? It's not immediately obvious. This doesn't take too much work, but we do need to prove it. So scratch work. So let n be a fixed real number. Recall, as we did just here, that A is congruent to B mod n when n divides A minus B. And of course, in order to work with this theorem, which is about congruence, we have to know our definitions. So please do make sure you remember these basic definitions, commit them to memory. Because if you don't know the definitions precisely, you're really not going to be able to prove anything. Okay? So it's very important that we actually remember definitions very, very precisely. So there are three things to prove here: reflexive, symmetric, transitive. So we really have three subproofs. And this is kind of using, if P implies three things, first one, second one, third one, then we can write the proof as like this. So first proof and the second proof and the third proof. So that's what we're going to do now. So let's first prove congruence modulo n is reflexive. So some scratch work. First thing to do is to remember our definition of reflexive. It means that A is related to A. So for all integers A, we need to show that n divides A minus A, because that means that A is congruent to A. Now, well, this isn't so hard. If we let A be any integer, then because A minus A is 0, which is the same as n times 0, we know that n divides A minus A, and so A is congruent to A mod n, as required. So we can write that up pretty easily. So it's going to be more or less just what we had there, just with a few more words to make it a bit easier for the reader to read. So we fix a natural number n and let A be any integer. Then since A minus A is n times 0, it follows that n divides A minus A, and hence A is congruent to A mod n as required. And that's enough to show that it's reflexive. Okay. Moving on to symmetric, well, what do we need to show? Again, we have to remember our definition of symmetric. It basically is what ARB implies BRA for any pair of AB. So we need to show for all A and B and n, if n divides A minus B, because that's what congruent modulo n means, then n divides B minus A. And so this is actually pretty easy, because this just tells you that A minus B is n times something. Well, then B minus A is n times minus that something. Okay, so here's our scratch word. Let A and B be any integers. We're proving this implication, so we assume the hypothesis is true. Then we reach the conclusion, because A minus B is nk, B minus A is n times minus k, which is an integer, so we know that n divides B minus A. Okay, let's write this up nicely. So we fix any natural number n, let A and B be any elements of the integers. We assume the hypothesis here, so n divides A minus B, A R B. A is congruent to B mod n, so A minus B is n times k. Okay, this is coming from the definition of divisibility. We've kind of skipped a step here. A is congruent to B mod n means that n divides A minus B, which means A minus B is n times something. So we're just skipping a little bit of stuff here in this proof, assuming that the reader understands that, for some integer k. Now, that tells us that b minus a is n times minus k, so n divides b minus a, and thus b is equivalent to a mod n. Just what we needed. So we've proved that if a is related to b, then b is related to a, okay? Giving us the symmetric condition. Finally, let's look at transitivity. So remember, transitive means a are b and b are a implies a, not b are a, let's go backwards here. B are c implies a are c. Okay? So we need to show for all a, b, and c, if a is congruent to b, that is n divides a minus b, and b is congruent to c, that is n divides b minus c, then a is congruent to c, that is n divides a minus c. So let's go through this. Let a and b and c be any integers. We assume this hypothesis is true, so n divides a minus b and n divides b minus c. Well, by definition, that means we know a minus b is n times something, and b minus c is n times something. Well, we need to say something about a minus c. We can just add these two equations together. The b's will cancel, and we'll get a minus c is n times something else, which is k plus l. We just need to write it up nicely now. So, fix an integer n, let a, b, and c be in z. We're going to assume the hypothesis that we need for transitivity, namely a are b, b are c, that's true. So a is congruent to b, b is congruent to c. The definition of congruence tells us that a minus b is divisible by n, and so we can write it as n times k. Definition of congruence again tells us b minus c is divisible by n, so write it as n times l, sum k and l in z. Well then, a minus c, just by adding these two equations together, is n times k minus l, so n divides a minus c, which is just congruent modulo n, just like we needed. Okay? So we'll stop there.